Hello, my name is Gabriela Imre, and I am working as a research engineer at the live cell imaging facility at Karolinska Institute in Sweden. In this video, we will explain what saturation and underexposure are, how to detect them, and why we must avoid them. What's wrong with this image? At first, it looks like the two channels on the right are too dim, and the channel at the bottom left is fine. However, there is a hidden problem in this image. The channel on the left is saturated. This saturation will prevent you from interpreting the information in these areas correctly. When you hover the mouse over the image, showing the overlay of the three channels, you can see the intensity of each channel at the bottom of the screen. These numbers are the XY coordinates in that point, and these are the intensities of each channel at that point. Here you can see written 3 × 12 bits, which means that each channel is a 12-bit image. We will now explain what this means and why it's important. The bit depth corresponds to the maximum number of levels of gray that the detector can acquire. 8-bit means 2 to the power of 8 levels of gray, which equals 256. So when the detector records an 8-bit image, the intensity value in this image may range from completely black, which has an intensity value of 0, to completely white, which has an intensity value of 255. Altogether, 8-bit images have 256 possible intensity levels. All the pixels with an intensity value between 0 and 255 are gray. Similarly, a 12-bit image may display a maximum of 2 to the power of 12 levels of gray, ranging from 0 to 4095. The bit depth minimum and maximum values are different from the actual minimum and maximum intensity values in the image. The bit depth tells us about the possible intensity values that the image can have. However, as we will see later, we aim at avoiding pixels with an intensity of 0 or an intensity of the maximum bit depth. Recording at a higher bit depth means that the finer intensity details are recorded. Additionally, high bit depth images have a wider range of possible intensities, so they can record accurately very low intensities as well as very high intensities. 12, 14, and 16 bits files have the same size and are double the size of an 8-bit file. It's important to remember that images with a high bit depth can only be opened by specialized softwares like Photoshop, ImageJ, or the microscope softwares. 8-bit images, on the other hand, can be opened by usual softwares like PowerPoint, for example. But when acquiring images in 8 bits, fine intensity details will be lost, and this cannot be recovered later. Also, you will have a higher risk for saturation. When analyzing your images, it will be harder to set the threshold. Keep in mind that the bit depth is not the maximum intensity in the image. It is the maximum possible intensity in the image. If the image is not saturated, its maximum intensity is below the bit depth maximum. In order to see if an image is saturated or underexposed, we can apply a color mask onto the image. In NIS-Elements, to apply the saturation and undersaturation mask, push this button. This mask will show in red the pixels that have the maximum intensity values, and in blue the pixel with an intensity value of 0. In this 12-bit image, we apply the saturation mask. In the image, all the red pixels have the same intensity of 4095, the maximum possible bit depth. However, it is likely that in reality, there are intensity variation in those areas. But because the detector is saturated, it is not able to record fine details in the bright region of the sample. The intensity information recorded in the saturated area is incorrect. Always set the acquisition parameters so that you have no saturation at all in the area of interest. In the same way, the pixels with the intensity value of 0 are color-coded in blue. This is called underexposure or undersaturation. In reality, it is likely that the corresponding areas have slightly different intensities. No relevant information is acquired for undersaturated pixels, and no details in these areas can be visualized. Thus, fine intensity details in the dim areas are lost. In addition, the objects in the underexposed areas will appear smaller. Always set the acquisition parameters so that you have no underexposure at all in the area of interest. A very useful tool in visualizing the pixel intensity distribution in your image is the intensity histogram. This is a graphical representation of the image intensity profile which plots the number of pixels in the y-axis versus their intensity distribution from 0, which is black, to 4095, which is white. In NIS-Elements, you can find the tab for the intensity histogram under Visualization Tools. Right-click in the background of the software, and under Visualization Tools, you will find the Intensity Histogram tab. If you click anywhere in the x-axis, you will be able to read off the number of pixels corresponding to that particular intensity level. In this case, we can see that at the end of the intensity X, at the maximum value of 4095, we have no pixels from the blue and the red channels, but we have many pixels from the green channel. Similarly, if you move towards the beginning of the x-axis, towards lower grayscale values, we can see that we have many pixels from the blue and the red channels displaying intensity values of 0, and no pixels from the green channel. Also, when looking at the histogram, we can get a pretty good idea about the overall pixel intensity distribution in our image. And in our case, we can clearly see that we are very much lying on the lower grayscale intensity levels. So what we would aim for in our image is to have pixels covering the whole scale of intensity levels, but without over and undersaturated pixels. After readjusting our acquisition settings at our microscope, here is our new image. Our acquisition settings now removed any over and undersaturated pixels and shifted the distribution of the intensities towards middle grade values. Many of you are using ImageJ or Fiji for image processing. Before starting your image analysis, you should take a careful look at your pixels intensity profile in your image using the histogram function. You can find it under the Analyze tab. The histogram will show you your minimum and maximum intensity in the image. Very often, after we have focused our sample with the eyepiece and we acquire an image, the image is completely black. The reason for this is that the eyepiece and the scanning system do not have exactly the same focus point, so our sample is slightly out of focus. To be able to refocus, we need to see the dim information in the image. For this, we should increase the contrast and brightness in the image, and we can do this by pushing these buttons. This is called auto-scaling. Now we see where the sample is and we can refocus easily. Changing the contrast and brightness in the image only changes what the screen displays. The data in the image is not changed. There are several ways to push the contrast and brightness in the image. This button pushes the contrast automatically for the current image and keeps these settings for the following images. Use this button to keep auto-scaling for each image. Once the auto-scaling is set, this one toggles the auto-scaling on and off, and this one resets everything. The same buttons are found under the Lookup Table tab. If you have pushed the auto-scale button, you can see there the minimum and the maximum intensity in the image. Additionally, you can change the contrast manually for each channel by sliding the black and the white triangles. If you want to set several images to the same contrast to compare them, you can double-click on the minimum and maximum and type a number. As I said before, changing the contrast and brightness in the image only changes what the screen displays, not the data. So when the contrast is pushed, what you see in the screen does not reflect the data in the image. This may trick you into thinking that your acquisition settings are correct when your image is actually very dim. To judge if your settings are correct, first reset the auto scale to display the whole range of gray levels. This is what your image really looks like when the contrast and the brightness are not increased. Then click again on the auto scale button to see the actual minimum and maximum intensities in the image. The maximum intensity should be as close to the maximum bit depth, but it should be below the value to avoid saturation. And as always, keep the over and under saturation color coding on at all times. In image J, you can adjust the contrast and the brightness of your image here. By sliding the contrast and the brightness bars, you will change these parameters in your image. Only save these changes on a copy of your original data, because once the Apply button is pushed, the operation cannot be undone. Always mention these changes when you are publishing your data. Another tool to change the brightness in the image is the gamma value, which is often shown as the letter G. The gamma of an image can be changed manually in the histogram by moving the little ball in the middle of the line between the minimum and the maximum intensities. Sometimes, if the sampler has dim features as well as bright features, and both need to be clearly visible in the image, pushing the brightness to reveal the dim areas will lead to the bright areas looking saturated. The details in the bright areas are not visible anymore. In this situation, it is best to adjust the gamma of the image. When one changes the brightness and contrast in an image and leaves the gamma as it is, at its default value of 1, the same changes are applied to all pixels in the image. The intensity of the pixels in the image reflects the brightness of the fluorophores in the sample in a linear manner. Therefore, if area A in the image looks like it's brighter than area B, you can safely conclude that the sample fluoresces more in A than in B. This is not the case, then one changes the gamma. Lowering the gamma below 1, for example, will make dim pixels look brighter, but the display of the bright pixels will not change. So with a low gamma, areas A and B might appear of the same brightness, when in fact they are not. All the display adjustment can be reset in NIS-Elements by pressing the reset button, but this is not the case in all software. In ImageJ or Fiji, you will find the gamma function under Process and Math. As always, save the changes on a copy of your original image. In conclusion, remember that the bit depth is not the maximum intensity in the image, it's the maximum possible intensity in the image. When setting your imaging parameters, you should set them so that you do not have any saturation or underexposure at all in the area of interest. Remember that increasing the contrast, brightness and gamma doesn't change the data. It only changes how the data is displayed on the computer screen. Remember that unlike NIS-Elements, when you are changing the display in ImageJ or Fiji and you are clicking Apply, this will not allow you to reset the display to its original. So when using ImageJ or Fiji, only change the display on a copy of the original image. Change the bit depth from 16 bits to 8 bits to be able to open images in non-scientific softwares. Never change an image to a higher bit depth. It artificially creates data. And only change the bit depth on a copy of the original image. Keep the original intact. You must always mention in your paper any modification you perform on your original image. Thank you for your attention.